Hi there. Welcome to another lecture. And today we're going to be talking about graphing. We're going to be doing some graphing interpretation, understanding the best way to graph and the best graphs to use and kind of basics of what graphs are. We're going to learn a lot more about how to graph. We're going to do some good graphing in some of our labs and things like that. So we're going to go into more detail later on. But just today, let's just kind of dive a little bit into graphing and into scientific notation. Great thing, two of these things, these are both great tools. The first thing is graphing, and we as scientists use graphs all the time. As consumers, you're using graphs all the time. The media, the commercials, the products, we get graphs inundating us, and so it's important that we understand what graphs are. So it's a super useful skill to pick up here today. And then scientific notation is going to help you to write numbers in much easier ways sometimes. So we'll dive into that as we go here. So our objectives here for today are to look at our three different types of graphs: line graph, bar graph, and pie graph. And then we're going to generate some of those, and we'll do the practicing of the generating. We're going to do that in class a little bit more. And then we're going to convert numbers into scientific notation. These 2 points here we'll get into later on. So today we won't hit those, but we'll hit them in another lecture. All right, so why do we organize data? There's a few ways to organize data. You can organize data either through a table or a graph, and various different types of graphs we can use. We like to find patterns, all right? So as scientists, we like to look for patterns, we identify patterns, and that teaches us things, right? We learn things from that. And we are going to use these things in written and oral presentations as scientists and as marketing individuals or just as business people. And remember, I just want to make sure you guys know the difference between tables and graphs. The table is something that is going to have a grid with a bunch of numerical data or written data, written information in it. Could be things like colors or whatever, but it's going to be a grid with different pieces of data set inside. And the graph is different, right? This is a visual representation of data. And so graphs are different than tables. Try to make sure that you're not confusing those two as you're going through. All right, so here we have a line graph. And you'll notice that this line graph has actually got some curves in it, and that's okay. It's actually very common to have curves in a line graph, all right? We're using line graphs to display data that changes. We want to see the change over time or the trend over time. And I want you to kind of understand that these are mathematical functions, that lines should probably be such that a mathematical function could represent them. The 2 points that you might have here, there's an infinite number of data points in between those 2 points. And that's one of the things that makes a line graph unique. And one of the things that makes a line graph one of the best graphs to use is it can be expressed as a mathematical function, and then you can interpolate, figure out what pieces of data might exist between 2 known pieces of data, okay? So in this particular graph, we have volume measured over time. And so you can see some of the things here. We're going to look at some of these variables. We're going to look at some of the units, and we're going to try to interpret some information from this graph here. So let's start with this first question up here. What are the x and y axis variables? All right, so identifying your x and your y. Your x-axis variable is time with a unit of seconds, okay? Your y-axis variable is volume of gas with a unit of milliliters. Very important that you understand that those are variables, and we're going to talk about what kind of variables those are as well. So let's look at these questions. Which variable is independent versus dependent? Now remember that these names basically mean dependent upon something else, okay? So if it's a variable that's dependent upon another variable, then it's a dependent variable. And then if it's going to be something that you measure, okay, or something that you're observing, or controlling the observation of, I should say, then that's your independent variable. So think about this graph. Which one, if you were looking at a balloon and how the balloon was changing its volume over a period of time, which one would you be controlling? Would you be controlling the amount of volume, amount of gas that's in that balloon? Or would you be controlling the increments at which you were measuring? The increments at which you were measuring is what you control. So time is the independent variable, and the volume is going to change based upon the amount of time that you're measuring it for. So the volume of gas is the dependent variable, okay? So make sure you know those. We typically put the independent variable on our x-axis, and we put the dependent variable on our y-axis, okay? That's a standard practice in science. All right, so we've done that top one. Why write units? Because, if this is liters, that's going to be a totally different relationship. And so we have to make sure that we know what our values are. Is that seconds? Is it minutes? Is it hours? Those would be very, very different experiments, right? So we can also interpret what's the volume of gas at 40 seconds. Now we call this interpolation. We look on the graph, we try to figure out what's there. In this case, we actually have a data point, right? So we have 40 seconds. We can see there's a data point there. And we kind of work our way over to the side there, and we say, hey, it's probably, maybe 23, 24, 25. It might be nice to be able to have a little ruler, kind of measure that, but right in that range there. At what time did we have 120 milliliters of gas? And then we have to go up to the 120 milliliters. We have to move our way over and see what time it is that we're at. Oh, about 90 seconds, right? And so you start with the volume, you move your way over, and then down wherever that line intersects, you drop it down, and you'll see what that value is, okay? What was the highest volume? Well, we want to see what's the highest number we got to on the volume, and so it looks like we kind of plateaued somewhere at 155 or so, right? And then let's go down to the bottom one. What is the general trend in the volume of gas collected over time? So is that general trend increasing or decreasing? Okay, the general trend is that it increases and then flattens out. And so it's important to look at trends, right? That's the whole idea behind line graphs, is we can see the trends in over time. Okay, so increasing and then flattening out. All right, so let's go on to our next one. Now, I want to talk about a couple common mistakes that we might have when we're making line graphs. And so try to avoid these errors as you guys are making your graphs. First one is not starting at 0, okay? So sometimes, let's say, this is, 20 and this is 10. That's not something we want, okay? We want to always start our graphs at 0. Now, in statistics, you're going to learn about a method where you can kind of do this, and that says, hey, we're actually going to start at a number that's not 0. In science, we typically don't do that. We want to make sure that we're representing the data as accurately as possible. In marketing, they're going to do something like, they'll be like, oh, that's 100, that's 110, and they're going to have that number there. So like there's only a small little difference, but they make it look a lot bigger. In science, we want to make sure it's as accurate as possible. And so we try not to do anything but start at 0, okay? So we want to make sure that's a 0 mark, and then whatever our values are from there. And if we have to go to 110, we're going to go way up there, and you're barely going to see any difference in, those two numbers. But that's the science of it. That's the reality of it. It's not going to seem as big, but that's a little bit closer to truth. All right, other things. Connecting the dots, okay? So that was one example. Let's go ahead and start at this next one. Connecting the dots. So let's say I have dots here, 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 and here, and maybe it's here. And so some of you will have practiced doing this, where you're making these little jagged lines, and that's actually not what we want to do, okay? When we are making graphs, we don't want to connect the dots. We want to find best fitting curves. So we want to try to figure out how would that data actually exist if it were actually moving like that. And so you're like, hey, yeah, it's starting at 0, and then we kind of curve through if they're actually a curve, okay? But that should be if it's actually a mathematical function. But it also might be that you just draw a best fitting line. And so you kind of have to figure out which one is it going to be. Is it more likely to be a best fitting curve, or is it more likely to be a best fitting line? And if I see something like this, it could be something that flattens and goes out, but I have to look at what the actual experiment was. Does it make sense that this would have flattened? Was there something that would have explained that? Or maybe we just had some really bad data. And so what we do sometimes is we have data points that are not really fitting in the story. And so we try to take a ruler and we try to say, okay, where can we find the average of these data points? While we go through 0, where can we get it to where we have about the same number of data points underneath the line as on top of the line, where it kind of averages out? And that's a best fitting line. And that's what we actually want to practice in this class. So you should either be creating best fitting lines or you should be creating best fitting curves, okay? But don't connect the dots. We don't do that anymore. That was old school. And then sometimes we have poor interpolation, trying to create data that likely didn't exist. So for instance, let's say, I had a dot here and a dot here, and maybe I had a little dot, here, something like that. And then I had another dot over here, and I'm like, oh yeah, that thing went like this, and then it went up like that. This is just completely crazy, right? I mean, that's faulty data. It's not like it would have really jumped up and then gone back down. And so this would be a poor interpolation. You usually don't see students do something as extreme as that, but you will see students that will actually kind of just add a little bit of a hump here and there when there's no hump. Typically, it'll be something where, you're here and you're here, and then it kind of comes over like this. And instead of showing it flattening out directly, they'll kind of go up and then they'll kind of come down instead of saying, no, it actually just kind of curves off like that. So you do see that kind of thing occasionally. All right, so we're learning a lot about graphs here. So that was a line graph. This is a bar graph. And there are better times to use bar graphs than line graphs, right? So sometimes it's going to be appropriate to use a bar graph, sometimes a line graph. Now, bar graphs are used to compare groups, okay? So individual items, events, or groups. So if your data is in groups, we want to use a bar graph, okay? So here I have got different types of elements that are present in, something that they're testing the melting point of. So this is something where we would actually use a bar graph because we can see, hey, they have distinct data and they're not connected. There's no trend that's connecting these over time, right? These are not connected data in terms of related to each other in a single mathematical function. So this is perfect for a bar graph. And that's what you want to do. Look for groups or items or events, and then that's what you're going to use bar graphs for, okay? And then we have pie charts, okay? Or circle graphs sometimes, you'll see them. And this is where you always are going to have 100%, a part of a whole. So you want to think about the fact that you've got 100% of something. That's when you're going to use a pie chart or a pie graph, okay? So in this case, what is the components of this person's coat? And so it's made up of this and that, this percent, that percent of those different things. That's when you use a pie graph. All right, so which type of graph would be best for comparing seating capacities of various baseball stadiums? Okay, so think about it. In fact, maybe you want to hit the pause button, answer these questions briefly, and then unpause and see how you did. Okay, we're going to go ahead and go through, and we're going to answer them, though. Various baseball stadiums, okay? They're different stadiums, and so we're going to have different groups, and so this is going to be a bar graph. Predicting missing data, right? That's called interpolation. If you want to predict or inside the points, or if you want to predict outside the points, it's called extrapolation. But this is going to be a line graph. We want to predict with lines. Plotting percentages of movies in the following categories, okay? So if we're talking about, what percentage out of all the movies are drama, et cetera, that's a whole would be all the movies, and then these different categories would be percentages. And so this is going to be a pie graph, right? A pie chart. Finding the trend in daily high temperatures at a local ski resort in the month of January. So this is looking for trends, and this one's actually a little bit tricky because sometimes we can see line graphs used for temperatures where they're not actually related points. And so, I actually would argue sometimes that it would not be good to use a line graph for something like this because you could just as easily see if there was like increasing temperatures with a bar, and each of those different bars are actually different days, right? The problem with using a line graph here is that you might be getting something like that when really, in actuality, the temperature is actually doing this every day, right? It's actually fluctuating up and down as it cools down at night, et cetera. And so the function is actually something different. The mathematical function is actually different than, it might be interpreted if you actually just drew the line and said, oh yeah, it's straight increasing. So anyway, this one, I'd probably accept either answer as an argument. You could argue why this one might be better or why this one might be better. My personal preference would be that this would be a bar graph, even though you are trying to look for trends. And you could say, well, I'm looking for the daily high, and so what's the trend in high temperatures? And you could try to, make a connection there. I'm totally okay with that as long as you're looking for trends in particular. But that's an arguable one, right? Always fun to have things to argue about and debate about and try to choose between. Okay. So that brings us to scientific notation. So I want us to talk a little bit about scientific notation, and then we'll take a break for today. So we've got different numbers here, and I just want you to, think about what these numbers are. If you were to throw these numbers into a calculator and do 10 to the 0, 10 to the first power, et cetera, you would get numbers that I think you're probably familiar with. Most of you probably have done something like this and know this. 10 to the 0 power is 1. 10 to the first power, well, it's 10, just 1 10, right? So that's 10. 10 to the second power, that's 10 times 10, right? And so that's going to be equal to 100. And if we did 10 to the third, it's 10 times 10 times 10, which is equal to 1,000. Well, we're going to go the exact same way down at the lower end of this, but we're turning them into fractions. So that's 1/10 or 0.10, right? This would be 1/100th, or we could write that as 0.010, okay? Or we could do 1/1000th for 10 to the negative third, and that's going to be the same as 0.0010, right? And so these numbers, using these exponents, those numbers are going to indicate values to the factors of 10. Well, scientific notation is a great tool because it is taking and putting numbers in a note form. Okay, so that's kind of the idea here. It's a note form or a shortened form of the actual number. Okay, just like you were to take notes in class and you might have a shortened form of all the stuff that I said. Well, this is a shortened form of a large number, or a shortened form of a very small number that would take a while to write out. The idea here is that we use scientific notation to express really large numbers or really small numbers in a much quicker and easier method. And these little numbers here, these exponents, are what we use. All right, scientific notation uses exponents to indicate what's happening. Now, I want you to learn, I'm going to teach you on this next slide, I'm going to teach you about the Powers gun method, okay? And so it's going to basically be a way where you can hold your hands in a certain way to help figure out whether or not your exponent should be going up or down and whether or not your decimal point should be going left or right, okay? So we'll practice that on one of the ones we have here. But keep this stuff in mind. This is a kind of like a grid showing what's happening in terms of how the numbers are increasing or decreasing, okay? So we already talked about why we use scientific notation. And I want to take this number and I want to explain my little gun method here. So what you're going to do is you're going to take your right hand. Okay, I'm not sure if this is reversed on the camera or not, but take your right hand and you're going to turn it into a regular gun, okay? And then you're going to take your left hand and you're going to kind of go as like an inverted gun, right? You know, you see sometimes in the movies are shooting upside down like this. Be cool. Well, now you're going to take those two. Okay, so right hand here, left hand on top, upside down. And now this is like a movie box. Now this is what you're going to use on the number to be able to figure out what you should do with it. So let's take this and let's look at it. Okay, so I've got a number here, and it's this really long number, and I need to put it into scientific notation. And some of you guys know this already, and so you're going to be like, yeah, I can say that. I know it's off the top of my head what it is. But some of you guys are like, I never know which way I'm supposed to move that number, and it's always really confusing. Well, remember that decimal points are always, if it's a whole number, it's always at the very end for our right-hand side. Okay, if it's a number like this, where it's a fraction, then it's going to be over here on the left. Okay, so I want to think about what I want to do. I always, when I'm writing scientific notation, I always want one number to the left of my decimal point. Okay, so whenever you finish, and there are other ways to write it, but in typical scientific fashion, we always want just one number, not 2, not 3, not 4, just one number to the left of my decimal point. So I've got to finish off my number with just one. And so I've got to think, I need to get this little decimal point all the way over here, okay? So I've got to move it over. 1, 2, 3, and basically you're moving it over, okay? And you need to count as you're moving it over how many you're at, okay? 9, 10, 11, 12, 13, 14, 15. I had to move that little decimal point 15 spots over, so there's just one number to the left of that decimal point. And so now I got to figure out, well, is that to the negative 15, to the positive 15? What is that? Well, take your little gun. Okay, again, this is my right hand. Hopefully this is not inverted on the camera. And as I'm moving it, I move my decimal point. Your finger moves the decimal point. So your finger moves the decimal point this way, and that means that your exponent goes up, right? So this is the gun. Finger moves that way, exponent goes up. So I know it's got to be 1.25, okay? I don't have to write all those zeros right now, times 10 to the 15th. It's a positive exponent because I had to move my number up, right? So remember, we had that 10 to the 0 and then 10 to the first, right? So we're moving it up. All right, now, if I do this one, my decimal point is over here. So now I've got to use that other gun to move my decimal point over so that it is 1, 2, 3, 4, 5, 6, 7. Remember, one number to the left of the decimal point is where you want to stop it. So I have 7, and I moved it this way. My left finger, right, was pushing it over that way, which means my left thumb is dropping that number down. And so I have 3.64 times 10, and my number had to go down from the 10 to the 0 to the 10 to the negative 1, et cetera, going down. So I have negative 7 here. So you can use that gun method to help you figure out whether or not your exponent should be positive or negative, because it is confusing sometimes. I get a lot of students that will write a really, small number like this, and it'll be like 3.64 times 10 to the positive 7. So just double check yourself on that. Really small numbers should have negative exponents, right? Because they're going down into the fractions of those tens. Okay, does that make sense? All right. In class, we'll practice a few different problems when you guys come into class, or we'll do it online together. But we'll go ahead and stop there for now. Let's see if we can now answer these questions. Have we met our objectives? Do we now know the different types of graphs, and can we interpret them? Yeah, we're starting to be able to interpret them a little bit. Are we going to be able to generate them? I think so. And again, we'll practice that in class, but I think we'll be able to generate those just fine. And we'll have to for labs and things. In fact, there's going to be a resource, in case you haven't looked, there's a resource on the website, which will, it's called Powers Graphing Guidelines or Graphing Guidelines, and it goes into much more detail of how to make them. And then our last one, converting numbers into scientific notation. Yeah, I think you guys convert numbers into scientific notation. You can also do it the other way around too, right? So just a little bit of a thought, if I had 1.96 times 10 to the negative 4th, now I should be able to convert that into a regular number, right? And so I have to kind of go exactly do what I did before, but I've got to do it the other direction. I know I need to have this number, okay, because I want, and when I come to the final answer, I have to get to that 10 to the 0, right? When I'm converting it into a regular number, that's 1, right? 10 to the 0 is 1. And I want this answer to be 1. So how do I get a negative 4 to a 0, right? 10 to the negative 4 to a 10 to the 0. Well, remember, 10 to the negative 4 is down there, so I'm going to have to go up, okay? So I got to get my little fingers out, right? Got to get my little fingers out, and I got to figure out, what do I have to do to go up? Well, I need to go up. Therefore, I need to move my decimal point this direction, all right? I got to go up to the 0, so I move my decimal point that direction. And so now I'm moving this over 1, 2, 3, 4 spots. And I plug in the little zeros there. And so my answer would be 0.000196. Okay. Same thing would happen if I had a number I wanted to convert, and it was one of those bigger numbers, right? So in this case, let's say I had 3.94 times 10 to the 8th. Okay. Well, I got to think about where that 10 to the 0 was, and where 10 to the 8th would be. 10 to the 8th would be above the 10 to the 0, so it's got to drop down. Okay, so if I have to drop down, get my little numbers out there. Oh, I've got to drop down, which means I've got to move my decimal point in that direction. My decimal point's already right here. Okay, you can notice it right there. And so I have to move it over. So let me just kind of say, okay, 3.94. How many spots do I have to move it over? 8 spots. 1, 2, 3, 4, 5, 6, 7, 8. Let me put my zeros in those little spaces. And so now I can figure out, put my little commas in there to see how big this number is. And I can be, oh, that's 394 million. Okay? And so you can convert from scientific notation to regular numbers as well. Okay? So hopefully you've learned a little bit today, and we'll get a chance to practice that. Remember, this stuff can be on your test, so study hard and have a great day.